I'm going to briefly explain continuity. Continuity is important because with continuity we can determine if a function is differentiable at a certain x value, because you can't differentiate a function if it's not continuous at a certain point. For example, here, well, this is now the test for continuity. Well, fx is continuous in the point, you see, at a specific point, x equal to, this must be a, x equal to a, if the limit of fx as x approaches to a is equal to the function, the function's value at x equal to a, because this means x equal to a. Now, to understand this actually means three things. Well, first, we might actually consider the graphical meaning. On a graph, let's say you have a function like this, and there's an open space there. Then there, let's say this is the x is a. Well, there, where the x is equal to a, if you place that this function doesn't have a value, a y value, a fx value at x equal to a. So for example, this one won't exist, and therefore this function is not continuous. So it means for a continuous function there shouldn't be any gaps in this function. Then only then we know that this function is continuous. Now, algebraically, how do we determine, by doing sums, whether a function is continuous? Well, you have basically three tests. The first one is you must determine if a exists. Okay, so you must put the x value equal to a into the function, into the x values of the function, and see if it does exist. Okay, so that's the first test you do. The second test you do is you see if you look at if the limit of fx as x, let's make that a limit, as the limit of fx as x approaches a. Oops, that's an infinity. Let me just wipe that out quickly. Oops. Okay, let's try that again. So the limit of fx as x approaches a must also exist, and remember what that means. Well, first of all, we know that the limit of fx as x approaches a from the negative side is equal to the limit of fx as the x approaches a from the positive side. When this is true, then the limit of fx as x approaches a exists. And the last algebraic test follows these 1 and 2, and that will just be, is the limit of fx as x approaches to a, is it equal to, well, the function's value at x equal to a? Because if they differ, then it then it might be something like this. So you'll have the graph there, an open point there, then you'll have a dot there, because now, well, the limit might be equal to 1, but the function's value at, let's say, a, it is 2. So the limit is the same, the limit exists, but the fa is 2, and they differ, and then it's not continuous. So those two must be equal to each other for this function to be continuous.